Okay. It works. The cloud recording. Well, let's see, because the computer doesn't have enough space, so we have to record it online. So if the cloud recording doesn't work, it doesn't work. Okay, there's probably next time I will just put the USB. Okay, so I guess it's time. Please, our great pleasure to have Hans from BIMSA to give the seminar talk this week. He will tell us about ribbon tensor 2 categories from cobraided of categories. Welcome.
Thank you for the invitation, and thank you for coming to listen to what I've been doing for the past year, essentially, or part of what I've been doing for the past year. So yeah, today I'm going to talk about a little bit about like this notion of a higher notion of ribbon tensor categories in which you categorify from considering these categorified higher Hopf algebraic notions coming from physics. But I'm not going to go too deep into physics because that's another kind of worms. So the overview is that I'm going to motivate why I'm doing this essentially, which is to essentially lift 3D quantum topology to try to understand 4D through the lens of quantum field theory, let's say. And I'm going to just introduce very briefly rigidity and these ribbon structures for monoidal tensor categories, and also how we kind of the strategy towards categorifying these notions. And the key idea is that I'm going to start with, as I said before, this higher algebraic notion of Hopf categories, and it's going to be quote unquote cobraided. I'll tell you what that means later. And also has a dagger structure, so it's a dagger tensor category with a whole bunch of Hopf structures. I'm going to take the modules of it and then look at what kind of structures that appear in its 2 category of modules. And it should be a good candidate for what a ribbon tensor 2 category means. And the motivating result from one of my other paper, not this one, not the one I'm talking about, but the other one is that there's this so-called 4D Tuchin Simons theory, which is a derived quantum field theory, which does have that does host this higher Hopf category as essentially quantum symmetries. So it's very analogous to the Chen story, but this is kind of where this cobraided thing came from, and I'll talk about that a little bit later. But the main takeaway is that there's a way in which you can construct under after I tell you, what ribbon 2 categories are. There's a construction which you can do, which is this 2 categorical dimension, but it has this I guess quantumness to it. You can call it the quantum 2 categorical dimension associated to every object in your 2 category. So I'm going to use the notation in which this guy is after transformation, and 1 is the identity functor. Oops. On B, and the ID is the identity after transformation on. So yeah. So let's begin with the motivation. So indeed, we want to kind of lift 3D quantum topology. So to start with, there are different types of invariants that you can construct in 3 dimensions. Of course, we all know very well you can do state sum or you can do surgery, starting with either the Turing construction or variable theory TQFTs, and you can do surgery to get the Richtingen-Toraf TQFT. And the central algebraic input for either of them is the fusion. One of them for the state sum is the fusion category, pivotal, and also for the surgery theory, you have modulus tensor category, and then you construct decorated ribbon graphs, and then you get the Jones polynomial, and you do surgery. You get Richtingen-Toraf. And for the fusion case, you do state sum, you construct the stick-shape symbols on the tetrahedron, and then you do state sum to get the Turing invariant. So, and the central question is kind of to ask about like these guys, the algebraic inputs. So I would say historically, both of them came from quantum groups. So you have these UQG compact quantum groups, and then you can look at how you're able to use the structures of these quantum group module category modules of these Hopf algebras essentially to construct these TQFTs. So for the fusion case, you can just look at some Hopf algebra, let's say finite dimensional, semi-simple Hopf algebra. But for D, for the modular case, you take essentially a compact quantum group and you look at the finite dimensional representations, and the compact quantum group, when I say compact quantum group, there's a C-star structure, there's like all sorts of stuff you have to do analysis, and then you get like, you have antipole, not only that, but you also have the ribbon element inside, and that's why you get a whole bunch of like additional structure, just not just fusion tensor categories. And these are very kind of in the spirit or philosophy of this topological prime reconstruction, in which you can identify a Hopf algebra for which C is equivalent to the modules of that Hopf algebra. So indeed, what happens in higher dimensions? That's a very important question to ask. And one proposal towards this problem is proposed by Bies and Dolan, which is the categorical ladder, in which you categorify with underlying algebraic input, categorify these things, and then, of course, you have to lift the whole thing to get like a 4D TQFT. But the first problem is to understand how to categorify these guys. So you can categorify what you mean by fusion category. You can also categorify what you mean by a Hopf algebra. So you have a fusion 2 categories. I'll talk a little bit later about like what exactly do I mean by a monoidal 2 category or braided monoidal 2 category. And also Hopf categories. I'll define what I mean by Hopf categories, I should say. So kind of the state of the art at this point, what is known currently are these 4D finite state sum models, which are built out of fusion 2 categories, and they're now known as Douglas-Schroeder TQFTs, and there are 4 dimensions. And what is also known is that the relationship between these guys, or at least like linear semi-simple Hopf categories, how you can do two kind reconstruction to get a fusion 2 category. And that's done by one of my friends, David, from Ohio State, and also Tsinghua and his collaborators. But what is not known is, so it seems that we know a lot about like fusion pits, but what we actually don't know a lot are these ribbons, these higher notions of ribbon structure. So how do we understand? So these higher ribbon structures touch upon this two tangle hypothesis, which is the idea that so in the usual tangle hypothesis, the statement is that up to isotropy, the algebraic description of tangles in, let's say, R2 times the interval, that is described by what's called a ribbon tensor category. And similarly here, two tangle hypothesis says that you should have some notion of ribbon tensor 2 category in order to describe higher dimensional ribbons. So this is kind of described in more detail by this paper by Bies and Langford, but I'll talk about a little bit later how their construction is actually not exactly correct, but there's a whole bunch of nice stuff. But yeah, so I would say that the main goal of this project really is to construct something modular. So you have a modular tensor 2 category, but that's I'll just talk about the ribbon bit, and that's already like pretty complicated. So and indeed, like the strategy that I will follow is I'm going to construct like a quote unquote quantum Hopf category, like a higher quantum group type of thing. I'm gonna forget about all like the analysis that I do and stuff, but just look at the algebraic structure. And then I'll look at the modules and then see what happens. Right. So, okay, let's get into the details. So let's begin with essentially like a review of what we are really looking at. So this is a diagram which kind of lays out the outline of all the structures that we're interested in. So we have monoidal category, and we have a braiding. Let's say I put a braiding on it, and then I introduce this balancing function, which is the natural transformation from the identity to itself. So it satisfies certain balancing equations. But what's really important here is that from the monoidal structure, I can introduce a rigidity addition, which are just duals. So a monoidal category with duals. And then with duals, I can impose the topological condition. I can pick a trivialization of the level. Oops. And if you put all of these, like pivotality, and you put the balancing, this ribbon twist together, you get a ribbon function. And the ribbon function satisfies this ribbon equation down there. So, like the strategy is exactly to kind of, I'm going to kind of start essentially over here for the two category case. I'm going to start here, and I'm going to start adding stuff. And let's see what we get. Like that's essentially the idea. I'm going to focus on one particular instance of a braided monoidal cube category coming from the modules of the Hopf category. And I'm going to see what structures on the Hopf category is necessary for me to define these guys and for me to have like all the coherence with the braiding data. So that's kind of the idea. Okay, so let me kind of just give a brief feeling of how we perform categorification, or what one monoidal or braided two categories are. So recall that a monoidal structure on a category is that I have a structure which is given by a monoidal product, just functor, and its associator, which is could write it as a natural transformation between 3 copies of C to 3 copies of C, or 3 copies of C to 1 copy of C. So these are the structure that I put on C, and then the properties that the associator satisfies this hexagon axiom. So it's an equation that you can write down. Well, when you categorify the structure, you should replace this guy. Well, not replace, but you should introduce an additional layer of structure which witnesses the pre-existing property. And then you introduce a whole bunch of additional axioms which witnesses the coherence of the thing that you just introduced. So in particular, of course, a monoidal two category needs to have a monoidal product functor or two functor. Indeed, I'm going to introduce this thing called the pentagonator, which witnesses the pentagon axioms, which used to be a property before, but now it is a two-morphism, so it's now a structure. And that's not enough. To also tell you how the pentagonator is coherent. So now I need, like, the pentagon equation has 4 guys here, and the associahedron axioms have 5 guys. So it concerns 5 things in different ways in which how you can like paste these guys together, essentially. Yeah. So I didn't write it down because it's huge. It's a huge diagram. I'm not gonna write it down. So, and similarly for the braiding, once you have the structure of a monoidal category, you can tell it how you can tell how it exchanges the the monoidal product, and that's the braiding, and it has to satisfy this hexagon axiom. This braiding has to be coherent against the associator, and that's the hexagon axiom. So when you categorify, you also have to include a two-morphism, which witness this. So that's called an hexagonator. And then you also have to ensure that it's coherent. So these are the four E2 axes, so-called E2 axes. And you can find them over here, and they're even bigger than the associated axes. So here I put two diagrams, which essentially tell you the shape of the two morphisms, what I mean by pentagonator and hexagonator. But yeah, I'm just throwing in the two cells. So that's the type of thing that I have to do. Like I know previously what my properties are, but when I categorify, I need to put data or put structure onto my two category, which witnesses the properties I used to have, and then I give you additional coherence axioms. I'm going to do this not only for braiding, but also for the rigidity condition, also for these things. And that's, I would say that's kind of the tough part. So, but we'll see. Okay, so the strategy that I have been talking about is to, the goal is to map out the diagram that I showed you for two categories, and the strategy is to start with this higher algebra, this higher Hopf algebra structure that we have. And to begin with, I'm going to define this bimonoidal category, the old notion. But the idea is that I have a monoidal category, let's say C of linear, right? And I have a monoidal category, I have a comonoidal category. So all that means is that I have a coproduct and it's co-associative and I have a commutative. And that there is a, and they're compatible in the sense that there's a natural isomorphism, which tells me that I can pass these guys to the other side. And the sigma is the braiding inside two vector, or wherever C is. So that's, you just very naturally lift the data or the structure of these bialgebra to the categorical setting. And of course, these things are now data, and I have to tell you how they interact, but they interact in a very obvious way. So, okay, so the next thing I want to add is this antipode. So the antipode now becomes a functor, right? And the key thing I want to kind of keep in mind is that the functor is op monoidal and also op comonoidal, of course. And also it's equipped with invertible natural transformations like that. It's just the usual antipode axioms, and also some additional coherence conditions. And I call this thing a Hopf category. It's quite straightforward because I didn't tell you.
So that's
Yes.
to have some monoidal structure.
Yes. Yeah. That's right. So So there are so if you apply S to like a tensor product, there's a natural transformation which witnesses. Yeah, that's right. So and indeed, and if you stay in the very finite inclusion case, there's a kind of a finite semi-simple of linear. Linear is built in, but finite semi-simple of categories you can obtain from doing this two-type prime reconstruction.
So we know that for finding the numerical Hopf algebras, the antipode is probably unique in something. If you have a bialgebra, you have some kind of canonical antipode, right? This is unique.
Mhm.
Is there any uniqueness here for the, let's say, the Hopf monoidal structure? Is that unique? Or even
I don't know.
Is it Hopf unique? So,
I don't know, but so what I know from quantum groups is that if I give you quasi-triangularity, then you can prove that S is invertible, right? Yeah. But I don't know about unique.
I see.
Yeah,
Okay,
but
I'm
yeah,
just curious.
Yeah.
I want to know on what level it is.
right. So that I mean that's a good question, but I shouldn't say things that I don't know the answer. So, And so far, I would say so far, the things here that I introduced is quite canonical and quite well known, I would say. It's very like, you do categorical prime, categorical prime construction, and you get the thing that I was talking about. But I would say that the next thing is kind of like new. Something that I haven't seen people talk about is the notion of a cobraiding. So what's a cobraiding? Cobraiding is a tuple of this R guy is a bimonoidal isomorphism, which goes from two copies of C to itself, well, to themselves, and an invertible natural transformation, which goes from R composed with delta going into delta off. So, yeah, so again, this is like a higher notion of quasi-triangularity, right? But I'm like picking a natural transformation which witnesses the intertwining relation for the R matrix, so to speak. But also I'm remaining agnostic about what this bimonoidal isomorphism looks like, but there's a traditional structure in which I just make all of the structure that I introduced dagger under this involution here. And so notice that S is up monoidal, but this guy goes from C to C up. So you already from this kind of point of view, you already see like there are layers to the involution. Well, S isn't really an involution, but there are layers to like this, the kind of stuff that you can do to a Hopf category, because you categorify, there's an additional kind of notion in which it and because like the delta now becomes the value functor, and there are some unitarity
So
associated.
this now is a morphism of.
Yes, that's right. Yes, yeah. So yeah, these are like the layers of structures that I want to consider. So right, let's get into I turn it off. Okay, sorry. Yes. So let's get into where did this cobraided notion come from. So I'm not very good at category theory, so I can't tell you anything about like the universal construction, whatever. But what I can do is physics. So this cobraided top category notion actually came from me studying these Harry gauge theory, try to quantize it, and the underlying internal gauge group is actually a category called a lead Q group. And the main construction is that I'm able to give you a construction of the high gauge symmetries of quantum two Chen-Simons theory, which is like a very physical thing, and put it on the lattice. And yeah, you can show that, or you can kind of perform something, which I'll talk about later if I have time, but it's at the very end. I don't want to get into too much details about this, but the idea is that the high gauge symmetries, which now forms a category, and it is in fact a strictly cobraided Hopf dagger category, and it's linear, of course. And there's some very interesting things that arises from this construction, which is that I have so this kind of puts like a physical meaning, gives the structures that I have introduced previously a physical meaning, or even a geometric meaning if you wish. So this is very analogous to the fact that you can understand Hopf algebras from the perspective of topological orders, and how you can kind of put boundary conditions on the topological order, and look at how like the boundary annual excitations that condense onto the boundary, you can glue together and also split apart, and that gives you a Hopf algebra. It's very similar. It's very similar in that regard. And also, if you specialize to a lattice, which is essentially a PL1 disk, so it's just an edge which connects to one vertex in a loop, then I would understand this thing as essentially a categorified quantum group. So again, I'm hiding a whole bunch of like analysis that you have to do, but really the analysis, the type of analysis that you have to do has already been done by Crane again. So that's what this is. So this is the Crane eligible category, which is essentially a whole bunch of sheets with special, very nice structures, which allows you to control L2 sections. They're L2 sections, I should say. So these are models for this thing that I'm considering. And a very cute thing that you can notice is that this guy, by construction, has what's called skyscraper sheets as homogeneous objects. And they have also been used. This is like, I actually learned this from talking with Warren. So I didn't know when I was writing a paper, but it turned out that the same things have been used to construct TQFTs with Lie groups in this paper by Banfi. So seems to be a very kind of a natural thing to think about when you want to deal with like infinite dimensional Hopf categories, is to use sheets. And this slide is really for like people who are kind of really into TQFTs. So we have this kind of a schematic diagram of what's happening with the various types of TQFTs in 3 dimensions. You have Turabiro, or level 1 if you wish, for the corresponding topological order, and then also over there you have the Stick-and-Toref construction. And there is some sense in which you can understand Chen-Simon's theory or Stick-and-Toref as being anomalous. There's this parity anomaly underlying it, and also Turabiro as being anomaly free. But in 4D, what you can do is that you can perform a looping of these structures, and so all the arrows here aren't like proven. I will say these are folklore. The idea is that you dilute these guys and then you land here. And what's interesting is that you dilute this guy. For instance, you consider representations of nuclear subgroup, and you take the modules of that modular tensor category. You actually land here. Like you don't land over there, you land here. So when you take modules of this, you land here, which is like it. People say that's Crane-Yetter, but it's how you construct Crane-Yetter. So, but there's another thing that you can do starting here, which is I call homotopy transfer, which is like not a good name. It's really homotopified, in which I make my underlying gauge fields derived, and I land into this Chen-Simon sphere. So you can ask, how are these guys related? Right, so and that answer, that question is really a conjecture for something that Bias in his paper assume is true, which I don't think. He gave a pretty flawed argument for why this is true, but you need to prove it, I would say. Like this remains to be seen. But the conjecture is that there's a certain type of Chen-Simon's theory, which is this in SU2 or inner on the 1 and 2 group of the SU2 B group, Chen-Simon's theory, and you can map it, or this particular Chen-Simon's theory is equivalent to the SL4 premium. So I call that the bias conjecture, but Bias didn't phrase it like that. Just assume that it's true. But that's some very interesting stuff that could lead to like very interesting things, especially because like this guy, I'm not sure yet how that Chen-Simon's theory is anomalous, but it could be anomalous. But yeah, that was just a kind of a how do I say it? Like those are gifts, I guess, to people into TQFTs. All right. Well, so yeah, and let's get into the meat of the talk, which is that for I'm just going to take a cobraided dagger Hopf category, and I'm going to consider finite simple linear modules of it, which is to say I consider modules inside today, and that's it.
So the question,
Yeah.
in Chen-Simon's, you have a level.
Yes.
That means you have to take field to be recovering.
Yeah.
Why do you generic would be?
Because I like you can prove it from the perspective of Chen-Simon. That you can prove that you have to quantize the level. If you construct,
Yeah, so
Yeah.
if you go to the next level, it will not be an integer or something.
no, it's more like you first you write down like the compact quantum group, which describes your Wilson lines,
Okay.
put on the lattice, and then you construct scattering amplitude. It's at that level in which you construct scattering amplitudes, and then you consider symmetry of like the Chen states of these Wilson lines. And it's at that point that you quantize them, that you see that you have to quantize them.
So quantizing the level means you take the derivative.
No.
Same as, no, so quantize the level means you take integer, right?
Integer,
Integer level.
Yes,
You
yes,
have to do.
Yes.
You have to do.
yes, yeah. Mhm.
And what about now?
Now I so far I don't have to because I don't know how the level is quantized from future sinus.
Oh, okay.
Yeah. So what I just wanted to say before is that what you can do for just regular sinus is that you can write down the compact quantum group, which models your Wilson lines before you do quantization of them.
Oh, okay.
Yeah. But it's when you compute the correlation functions that you notice that I have to quantize them. So that's but because here I haven't gone to the level in which I can actually compute. Yeah. So but yeah, that's a good question because it needs to be answered. But yes, so there's this theorem in which if I have a bimodal category, then you can reconstruct all the braided monoidal structure for the two categories of two representations. And it's just a kind of a thing to do, right? The co-product gives you the monoidal structure and this guy gives you the braiding. So it's, and you just map out all the coherence diagrams and it works. So, but now, not only do we have a bimonoidal category, which is cobraided, we also have access to more structure, and they are geometrically significant. And the structures are indeed this dagger involution that I have, which is related to orientation reversal, and the antipode, which is related to framing rotation. So it's kind of like keep in mind this geometric intuition, but so far, you can just treat them as algebraic kind of structure that I have. And the idea is that, okay, once I include these guys into my module, my two category modules, then you can say that this two representation, two category is ribbon tensor. So let's see how that happens. Right? So indeed, like this is a warning that says, if you're really doing physics, if you're really doing Shin-Simons, then you have to be careful because C doesn't have to be in here.
So what is the regular representation? What is the notion of regular representation?
It's so from the let's say you do Peterball and then you construct,
Okay, yeah.
you reconstruct this side and
Yeah.
coed.
Yeah.
But then like for regular quantum groups, you have to take the coed over infinitely many irregular representations.
Yeah.
So you have to ensure that infinitely many. So you have to ensure that coed exists, which is the existence of certain limits, which I don't know if that limit exists in. I don't know if that's true. That's how the object, yeah. So to answer that question, of course, you need to like include all infinite limits into this guy, which apparently
These spontaneous are computer also.
yeah, exactly, yeah. So apparently, so I just came back from this meeting in earlier, and there's a whole bunch of string theorists over there. Apparently, they're able to answer that question. I don't know how, but apparently they're able. So. But yeah, so I'm going to start with the assumption that this module two category or two category of modules is two vector enriched. So the two morphisms are vector spaces, perhaps super spaces, but let's not think about that too hard at this point. So the main definition is that there's this notion of planar unitarity, which is probably not a very good name, but all it says is that I'm going to assume that all the functors I have in this two category, all the one morphisms I have adjoints, and the adjoints homotopically intertwine the dagger structure that I have in my Hopf category. And once you have that, because of the dagger injunction condition and also the unitarity condition on H itself, then I can write down units of the injunction and lift it to C module. So in other words, like these guys become C module natural transformations. So they actually do indeed live in here. And which is to say that, okay, so let's say I start with 2 back, right? I start with 2 back. All of this is true. Like I of course have these guys. One of them is a adjoint unit of these injunctions. But the idea is that, okay, now I throw in this C module structure into my 2 category. What conditions I need to impose on H such that I'm able to lift the units and also the injunction to C modules? And the answer is I need the adjoints, because now the adjoints have like, you know, they homotopically intertwine the action, the C action. And the condition is that the adjoints have to homotopically intertwine the dagger of C. So, and that's essentially the idea, is that this condition, then I have what's called planar pivotality. So planar pivotality allows me to perform these graphical calculus, but only at the level of Hopf categories, and only at the level of like 1 morphism and 2 morphisms. So sometimes these guys are just called pivotal bicategories by Jürgen and some of Jürgen's work on string nets. But this is not enough for me. I need more stuff, because I do have more stuff. So the more stuff comes in the form of the antipode. So as we know, I'm going to introduce duals on my 2 category, monoidal 2 category of 2 representations. Going to just throw in the antipode and use the antipode to define notion of duality. So this is just a formality, but this is just saying that the action, the C module structure on the dual is given by the antipode. And also the left dual, so I have a right dual, I have a left dual. Left dual structure is given by S inverse. It's kind of the canonical thing to do. And if you write down the antipode axioms, use the antipode axioms, I should say, then you're able to write down not only the duality data here, you have the evaluation and the co-evaluation, but you also have these guys, which are the guys that essentially allows you to perform to like swap F. So you have a evaluation and you're able to swap 1 morphism to the other side, and you take a dual. So these are not the adjunctions. These are the dual mates, right? The right mate of the dual on D. So you're able to swap this guy to the other side. So that's what the antipode axioms on the Hopf category buys you. And also you have a 2 co-wedge. So these guys, this data and also these data for all objects and 1 morphisms in your 2 category, they define for you what's called a 2 co-wedge. Because they 2 co-wedge into the identity C mod, C mod, yes. And moreover, you can also define the co-evaluation, which is a co-wedge, 2 wedge. This guy's a 2 co-wedge and a 2 wedge. And the antipode axioms tells you that you have this, well, it's just the usual, it's called snake operator. It's like the snake equation, right, for the evaluation, co-evaluation. But now you have to get it, now you have like a non-trivial invertible natural transformation, which homotopes between this and the identity. So that's why it's called snake operators. And there are these coherence conditions on the snake operators called the swallowtail equations. Something that you can write down. It's a big diagram, but something you can do. And these are, you can find like the graphical interpretation in Symmetry. So, and the key thing to note is that duals is only involutive only when the antipode is, well, no potent or is first to the identity, basically, which I'm not going to assume. I'm going to assume as little as possible. Okay, so now I have in my hand duality at the object level and also kind of quote unquote duality at the morphisms level, which is the planar pivotality that I had. I'm going to put them together, and all I'm going to say is that all the duality data are planar unitary, which is to say that they have planar pivotal adjunctions, basically. So I can take adjuncts of these guys. I can also take adjuncts of these, and they all live inside my tube category. And yeah, it's just a condition which ensures that I can take left duals and right duals and blah blah blah. And the idea is that okay, these structures, well, I take a dual and then I take an adjoint on one morphism, for instance, they're supposed to commute, which is that they're supposed to be naturally isomorphic to me taking a dagger and then I take the dual. So this is coming from this strong commutativity, essentially, between the dagger and the antithetical structure on my Hopf category. Well, it's a very natural thing to do, actually. If you and kind of imagine, going back to the physical case in which the Hopf category encodes for you these Wilson surface operators, then you can leverage geometry, and the orientation reversal analysis is this framing rotation to essentially conclude or arrive at the conclusion that you have this condition on your Hopf category. So there's the geometric interpretation of this strong commutativity result, and this is also in kind of explained briefly. This geometric interpretation is also explained briefly in Zheng Wei's paper last year, and also in this paper with 16 authors last year. That's the higher coherent dagger paper. And they considered exactly this condition, this sort of condition, which they call this a two-dagger condition. But their two-dagger condition has S being included. But I'm not assuming, right? So this is very nice. Why? It's because I'm able then to use the adjoints of the duality structure to write down decorated surfaces. So if you have this graphical calculus picture in mind, these guys indeed give you, like, I call this saddle morphism because it literally gives you a saddle. When you write down the morphisms, gives you a cap, as a cup, as a crotch. So saddle is like, it turns upside down, it turns upward, and the crotch turns downward. So, and when you have the cap and cup two morphisms in hand, then what you can do is construct the two categorical dimension associated to an object D. The way you do it is just you use the composition of two morphisms, the vertical composition of two morphisms, to glue together a cup and a cap. But what you notice is that you have to match the legs, right? You have to match the domain and the codomain. And one of the ways in which you can do that is to impose an additional condition, which is called strict pivotality. And this is what was done in the Schroeder. And the strict pivotality assumes that you have an equality on the nose of the double dual with the identity. And also you have strict equality of the dagger of the evaluation with the co-evaluation on the dual. But this is very strong because it hides too much stuff. So, and of course, this requires S squared to be 1 to be identity, which is too strict for my liking. Perhaps this is good because indeed it's too strong of a condition because the warning from forgot like the numbering for this warning, but it's warning 2.5, I think, in the Schroeder's paper. They say that their definition of two categorical dimension is also too strict or too weak, depending on how you view it. Is that the dimension is not invariant under equivalence of objects or natural equivalence of objects, naive equivalence of objects. If you just think of your underlying pivotal two category as a two category, and you take like pi 0, and you can change the value of this guy within one connected component. You can do that pretty easily, actually. So how do we fix this issue, right? This non-invariance of the two categorical dimension. Well, of course, now we can add the braiding to the story, and my claim is that adding the braiding will solve this issue, will solve this non-invariance issue, because it will tell you exactly what type of equivalence that you should impose such that you don't change the two categorical dimension. And it will tell you explicitly how to do it, because now with the braiding, you're able to define the canonical ribbon balancing functors. Now I can introduce the balancing, and it's a very canonical thing that you can do, in which you just, you write down the twist is like this, and you just write down all the morphisms that gives you that shape, and you get these two functors. You can do it in two different ways, which is kind of strange, right? But we'll see how they're related later. But all I'm saying is that, let's say I take this guy, right? I pick this guy to be like the canonical guy. And one thing I should say is that you can also prove that you have balancing equations, which is the coherence condition between this functor on the tensor. Oops. This functor on the tensor product, or the tensor product of theta d and theta d prime, for instance, that's the balancing equation, and you can write down two morphisms directly from the C module structure, which witnesses that balancing equation. So, and the idea is that, okay, now I have this guy, and I can define this, which goes from D to D double star, double dual. And because of this, and also this other thing that I would like to define, but it's like a two morphism, it's called a writing. So you can imagine if you draw, maybe I can draw a picture. So the writing is essentially, so this is, let's say, evaluation, and then this is the braiding. D star or something like that. Or co-evaluation. Co-evaluation. So, like something like that, something that on the evaluation, you're able to untwist things. That's what this is. So once you're able to have this ribbon structure, and you're able to define this guy for the writing, then you're able to define a more refined notion of two categorical quantum dimension. Because this guy came from the braiding, and then braiding came from some kind of R matrix, so kind of a quantum thing. But the idea is that to really define the two categorical dimension, like you have to shove some stuff in. So
yeah, very natural, right? So,
yeah.
A categorification of dimensional.
Exactly. Yeah.
The definition of quantum dimension for fusion category.
Yes. Yeah. But the idea is to really kind of pin down what kind of things you have to throw in, like what your generalized isomorphisms really look like.
Yeah.
It's not really obvious. Like I would say it's not obvious. So and indeed, like from this, and you can really give a definition of what's called a ribbon adjunction or ribbon adjoint equivalence. So these words also appeared in the Douglas Schroeder paper, but they really didn't define what it means. But here, what it really means is that it like this functor just centralizes the ribbon functor in a certain sense. Because if you can do that, then of course you can shove like something that you can construct on F here, and then you can move it back and forth. But okay, now let's move on to, well, not move on, but like to kind of understand the braiding a little bit better, or the co-braiding rather, a little bit better on C. So I'm going to make an assumption, which is to say that this bimonoidal isomorphism that I have is actually coming from an inner inner thing. So this inner thing lives in 2 copies of C. So it really looks like a R matrix. And I'm going to suppress the associator from now on. Then I can explicitly write down the cobraiding. And not only that, it also allows me to investigate when the 2 representation 2 category is symplectic or E3, because now you have a 2 category, you can have more levels of monodality. So you have E1, E2, and E3 before you hit E infinity. So it's a major question of how you can describe symplecticness from this kind of perspective. And if I give you a Hopf category, which is cobraided, and the cobraiding looks like this, then my statement is that, yes, you're able to characterize when your 2 category is symplectic. And that condition is this quasi-unitarity condition, which looks like this. So if you remember, like in the usual quantum group case, you have this unitarity of the R matrix, which is this condition, right? So the inverse is taken with respect to like the matrix inverse. But here, what I'm doing is I'm imposing a similar condition, but only for the dagger adjoint. I'm not using the anti-fold or the stars, the C-star structure or anything like that. But I'm imposing a similar condition at the level of the dagger junction. So, and then what? So you can imagine, like, I have that type of condition, and that unitarity tells me that there's some unitarity condition, which is sufficient for me to define something that is symplectic. And indeed, I can write down the synapsis, which is actually just given by one of the units of the adjunction of the braiding. So that's a proposal for how you can kind of characterize synapses for a monomial 2 pattern, essentially. Yeah. So and you can just run this through the module structure, and you see that I have this thing, and once I have this thing, I can give you this, and so you can trivialize that on the grid, and it should be coherent. Yeah.
The synapses should be a additional structure really category. So there should be an additional structure on C, so that the representation in 2 categories is symmetric.
Yeah. So the additional structure is this thing. Oops.
So you mean that that as a model?
Yeah.
You have to choose them as a model.
Okay.
Yes. That's right. Yes.
This price is a dynamic structure.
Yes. Exactly. Yes. So this is a taste of the size of the coherence conditions that you can write down. So here in this case, of course, a 2 category, the axioms look like 3 cells, or like empty 3 cells, I should say. So it's a bunch of 2 cell pasted all together, right? And the way that you paste them together is actually like it's crazy. Like you look at this, you normally you would not think of doing something like this, but it's actually like coming from, if you think of things really geometrically, and then you want to prove, well, not prove, but you want to instantiate the 2 tangle hypothesis. The idea is that in this paper, they wrote down something similar, but I'm just generalizing it to my case, in which I don't assume I don't assume a whole bunch of things that they did assume. So this is just one of them. So I have I think two other. I have another one, and I have the dagger adjoint version of those. So I have 4 in total of these big diagrams. And another thing that you can do is that, so remember the swallowtail equations. So I don't have to impose swallowtail equation that they are equal to 1. I don't have to impose that in general. I can just write it down as a, by one, I mean the identity, natural transformation. So I can just write it down as a two-morphism, it's a big two-morphism. But the idea is that with the introduction of the braiding, I can write down also this very big diagram. I can put the swallowtail morphism here, two morphisms, swallowtail two morphism, swallowtail two morphism, which remember concerns the snake equilibrium, right? So, and then what I can do is that I have this corner here, use the writing, and I can kind of wrap around each other, and I can paste it together. So that gives me a three cell. Sorry, not a three cell. Sorry, that gives me a two cell, which consists of a boundary of an empty three cell essentially. And my condition is that that big thing that I wrap around is the identity. So I call this the swallow case because it essentially entangles the two swallowtail morphisms together. But there's a funny name. But yeah, these are like the type of diagrams that you need to check commutes when you say that you have a braided ribbon tensor to them. But not only that, that's not all. So indeed, as you kind of mentioned, that there are these different isomorphisms, but that's when you impose like some notion of totality, right? But so far I haven't done it. I have just given you rigidity. I've just given you rules. I haven't imposed like any kind of like totality condition. So it will come up, but the idea is that if I have these balancing functors, theta and theta bar, I can give you how are theta and theta bar related. Well, there are these two isomorphisms, I would say, which goes between theta bar star and then theta pre-composed with star. So there are these guys that go between theta bar and theta. And this is for free, like you can just write it down. I don't have to impose any strict pivotality condition. And you can just write it down, and they're coherent against the balancing equations or balancing two morphisms. So now you notice that I have these guys, and let's say suppose I can identify somehow theta and theta bar, right? Then these guys gives me exactly what you expect for a ribbon structure. Remember, ribbon structure is theta of D star, theta of D dual is equal to theta of D dual. And when you categorify, you expect a two-morphism to witness that, right? So when you somehow can identify theta and theta bar, then you win essentially, in which you have these so-called Drinfeld modifications. And that will give you a kind of like quote unquote true ribbon structure. But this, of course, requires you to kind of also have this, right? Which is not exactly true, right? Because theta, as far as I have defined this balancing, it goes from D to D double double. Doesn't go from D to D. So I need some motivation to identify D with D double double. So the way that I propose to do this is to think about the geometry, like really think about the geometry, and to essentially match with geometry is that you just look at the Reidemeister one moves, and there are various ways in which you can construct Reidemeister one moves, which is a trivialization of twist. So if you have different ribbon functors and you impose certain coherence conditions in between the Reidemeister one homotopies, then you're able to kind of write down, you can essentially reduce the number of different ribbon balancing functors that you have. Distinct ones, I should say, up to isomorphism. And the first observation is that I can do this. Theta bar is the adjoint of this. I can do that. And this is coming from, there are two kind of different perspectives towards this, which is that I have this two Bradford isomorphism, so to speak, which is a trivialization of S to the fourth. on my Hopf category. In which case you're able to write down at the level of the modules the equivalence of left and right relative self filters. So once you have that, then you're able to write down this. You're able to introduce a modification which fills in that reset over there. So once you're able to do that, and then you impose this condition, which really comes from geometry, then you're able to construct a ribbon preserving three-morphism on the duality. But this is all at this point, it's just formality, right? But the idea is that at the end of the day, you're able to reconstruct this thing which came from this paper. And that paper is talking about these gray category with duals, and they argue through a whole bunch of like big graphical calculus diagrams, and then they construct this modification. And the idea is that I can run this condition backwards to say that provided you give me the two wrapper, let's say you let me assume that I do have the two wrapper isomorphism, can trivialize S4, then this condition can be obtained from this condition. So this condition in which you identify certain ribbon twist with an adjoint of another one, so that's kind of like a, I want to say SO3 evolutive or something like that. At least there's some action on the unit sphere or something like that, in which you can perform such that you obtain this isomorphism. When you have that isomorphism, then you see that it reproduces for you these structures of three categories of tools. And it's really a geometric thing. But now let's move on to, I don't know. Oh, okay. That's scary. But now let's see how this type of thinking can lead us exactly to this dropout modification that we have. So that we want, I should say. So now I'm going to impose pivotality. Now I'm going to choose the trivialization of the double dual. So this hash is the double dual. I'm going to choose this trivialization. Once I pick that, then I can yes. Then remember this gamma is like this, right? And once I have chosen this pivotality, then I can paste this pivotality together with gamma, with this diagram here, to obtain this shape. So I'm going to kind of like cheat and then call these guys still beta and beta bar. But now you see that beta and beta bar are really identified, and you can really kind of trace how they're identified. And the way that they're identified is indeed given this pivotality structure. And once you have that, then you exactly have that modification. So you have that guy which witnesses for you the ribbon condition. So this, I should say that, okay, once you've chosen this, you really have a ribbon structure. And it's over here that you really have like a ribbon tensor 2 category. And I will call like this guy here a lax ribbon 2 category, perhaps, maybe. But and down here, another thing that you can also check is like the well, it's a physical thing, so don't worry too much about that. Right, and also down here, so right, remember I said that this paper by Zambales and Langford, they studied similar ideas from the two tangle hypothesis perspective, but they made some kind of like not very, how to say, not very general assumptions, let's say. One of the assumptions is that they conflated the dual mates of one morphisms with the adjunctions. That's one thing. But we know that at this point, all we know is that they commute. on the one morphisms, but they can be different, right? But in that paper, they conflated both of them. And another thing is that they identified the Wedemeister one homotopes with the right. So that right thing over there, you draw it like a tangle diagram, then of course that looks like a Wedemeister one. But technically speaking, if I have access to these guys, I can define for you the Wedemeister one. I can just without taking the evaluation, I can do this, and I can just trivialize it without doing any evaluation or co-evaluation or whatnot.
But there's no move one in this.
In 3D now, right?
So that when we cross, there's a similar point.
No, but you can like untwist the top.
Twist.
Yeah, you untwist the top. Yeah. So that's like one of the I think well you do a rotation around like the great circle and so yeah, so
Oh, you can frame it and
yeah mhm. Yeah. So right, so well, there's some further reduction that you can do, in which indeed, like once you do all that reduction all the way down to the bottom, you only get one distinct ribbon structure, and that's exactly what Myers and Lightberg also had. They also wrote down one ribbon structure. Okay, to summarize, this is kind of the two categorical version of the diagram I had at the very beginning, in which I have monoidal two category with adjoints for one morphisms, all adjoints for one morphisms, and introduce braiding and introduce balancing. And you go down, but then now you see that once you introduce duals, and then you impose pivotality, and you pick a trivialization of the double dual, there are different levels at which you can pick such trivializations. I call this lax, in which like you have these guys. Oops, sorry. In which you have that, but once now you're down here, you have a pivotal structure, and then at the very end, you see that you have this two ribbon structure and a true kind of two morphism, which witnesses for you the ribbon equation. So also the one more thing that you can think about is that, okay, now I kind of think about spherical structure. So this is kind of schematic because even already at the pivotal level, there's a distinction between lax pivotal and the pivotal condition. So you should have a spherical and a lax spherical condition, possibly more. That's the thing. I have no idea how these different things are related, but if you just work through kind of like the different levels of the algebra that you have to do, and then you look at all the diagrams, then presumably you're able to obtain a notion of modular tensor two categories at some point. So, but that's the strategy. But I imagine that's probably going to take another 100 pages or something. So, but yeah. So indeed, at the end of the day, we want to realize or instantiate the two tangle hypothesis. We're speaking to a ribbon functor. That ribbon functor itself is an instantiation of the tangle hypothesis, in which I map representations of UQG into. I map the ribbon category of tangles. Tangles in R2 times the interval. I map that category up to isotopy into representations of UQG. But here I can do something similar, which is that, starting from Chen-Simons theory, I have these Wilson surface states. And the proposal is that these Wilson surface states are exactly these ribbon two functors, in which you can map the ribbon two category that Bias and Lightberg constructed purely from geometry and topology. A bunch of surfaces crossing each other, to map that into while preserving all the ribbon structure thing. And that should give you like a two-dimensional or surface version of the decorated ribbons of which they convert. And then you do surgery, which is another topic. But okay, so to summarize, there's some outlook for what we want to do, and one of them is indeed the quantization of the level, which is apparently somehow related to positivity of the global dimension. This is a statement I learned from in the categorical case, I should say. It's a statement that I learned from the paper by Alexa Shomerus and Rosa, in which they did combinatorial quantization of Chen-Simons theory. And they say that you can prove the quantization of the level from looking at the global dimension of your Wilson line states. That's their statement. But at the end of the day, yeah, indeed, we should try to understand how the levels quantize from the perspective of these 4D TQFTs. And also, another thing is we would also like, okay, you know, it's nice to have these two ribbons, decorated two ribbons and whatnot, but you also think about how you define the Torah-Bureau version. So the Torah-Bureau version just requires essentially a monoidal two category, but you do need pivotality in like the sense that you have object level and modism level pivotality. So you need a two category tensor monoidal with a pivotal structure, and then you're able to kind of write down kind of a state sum or membrane net construction for the corresponding two Chen-Simons TQFT, which essentially bypasses surgery theory. So you don't have to do surgery theory for Torah-Bureau. And this is just one of the things I want to highlight from Zhengwei's paper, which is that you have these he constructed these point J symbols, so to speak, from his functional integral construction. So maybe that'll be useful. I don't know. This is still work in progress. So yeah, more interesting stuff about this line of thinking is that you have this is just a restatement of the bias conjecture that I mentioned previously, and also the gray category of duals. And the statement is that these gray category of duals are supposed to label defects in a 3D defect TQFT. So that's very interesting because somehow we're able to also have very similar structures as gray category of duals coming from a 4D TQFT. So maybe there's some like relationship between Tuch and Simon's theory, and also you can think of them as, in certain cases, you can think of them as a theory of in 4D of defects in a 3D maybe. And also another thing, which is something that I get kind of away from all this categorical stuff, is some very field theoretic thing that I did, which is you look at the boundary conditions of this Chen-Simons theory, and you're actually able to find a gapless one. You're able to find a gapless boundary. So you can't do that for a quick error. That's how it is, right? You can prove that quick has Michigan Torah at the boundary, or Michigan Torah is a 3D theory at quantized level is gapped. So not much you can do there. But here for two Chen-Simons, what really substantiates my intuition that two Chen-Simons can be anomalous is that it has a gapless boundary. But the idea is that this is not a conformal field theory, it's not CFT, it's something called topological holomorphic field theory, something coming from like 3D S equals 3D N equals 4 SCFTs that people think about, but you know. But yeah, the idea is that I would say this 4D theory has a whole bunch of like different stuff that you can look at, and possibly this thing has higher dimensional notions of integrability, similar to the cosmology BOA, so where familiar with, without thinking about the Westermann width CFT, you can write down the classical R matrix, and you're able to perform, like, you can write down the Lax operator, and then the R matrix, and then you can say that it's infinitable and construct like a whole bunch of different infinitely many charges in evolution. And something similarly can be done here, actually. You can write down infinitely many conserved charges. But what really controls the integrability of those charges? That's like in progress, work in progress, but also a very interesting question. So, well, that's it. Thank you.
Thank you very much for the very good talk. Any questions? I have asked a lot.
Yes, yes.
Yeah.
Very naive, more philosophical question.
Mhm.
So you say your goal is to define what is the rank one of the modular N2 category.
Mhm.
Do you expect the distance of a modular 3 category or category, and do you think it's even more and more complicated, or do you expect a distance of a global understanding for any modular N category?
Mhm. I think that question would be as difficult as finding representations of mapping class groups of 3 manifolds, 4 manifolds, etc. Yeah, and I think it would get more. It would get more complicated. Yeah.
So at one moment, which may be more non-understandable for human brain.
Oh.
It would be too complicated. We need some AI.
Some AI. I don't know. Maybe. Yeah. I don't know. Yeah. But I might be the wrong person to ask. So.
So for the last thing, after this thing, do you think it's a categorification of VOAs, which is that we're looking at?
Well, that's a good question. Depends on what you mean by categorification. Right. Yeah. So if you say that I have a Hopf algebra or not Hopf category, sorry, a similar kind of Hopf algebra, categorical VOA or something like that, then I would say no. What you really have is a derived thing. You have a derived.
Yeah, that's also some kind of categorification.
Yeah. That's true.
Yeah.
But it looks completely different than what I was just talking this talk. Like that's a completely different story.
Yeah.
Yeah.
That's
Yeah.
would be helpful.
So you get a scalar, you expect you have a scalar invariant for manifold.
Yes.
So is that's manifold, that's why is that invariant is expected from some kind of like function silence, and then you have some action.
Function silence, and then you have some action.
From the classical
Are you thinking of like are you thinking of you have like a family of three function silence and you have the global symmetry of some kind?
No, it's talking about the intense silence theory.
Yeah.
Right, you have three manifolds, you write it as a surgery, and then you integrate along the surgery link with the action into the action, and then you get an environment.
Right.
Is it also truly important? Where
Are
you
you-
describe a four manifold by something and you integrate the action along the thing.
Yeah. I think that should be also what we should do. Yes. But yeah.
What's the gauge group?
It's a gauge 2 group. Gauge 2 group, yes. So, well, so this is something related to this thing that I'm working on, in which that what you're really studying are like what you're really doing is like you are well okay, so let me write down. So you have this flat. Let me just write it like G, let's say, and now of course this guy is like, you know, the character variety or I should say pi G and then you like you're asking about this guy, right?
Yes.
Yeah. So right, there should be something very similar that you're doing. Like indeed, like you have now you have a two group, and now you perform essentially group point quotient, perform a homotopy fixed point, get the homotopy fixed point of this guy, let's say. And then but the idea is that you should really think of like kind of the space of all arrows instead of keeping track of all the objects. But you got
So I think there's a issue of the components designs for the theory that originally we can say that the group G is actually true. That means it's compact group.
right.
Recently, people realized that actually sometimes you can do the downward conjugate or something in the TC part, right? And sometimes you compute some quantities that are not expected from as you deal with. Example, volume conjecture, right? So the volume never comes from S2 example.
Right.
It actually come from the SL2C.
Right. Yes.
I don't know if there's another thing here that you do also have the notion of compact and non-compact. Something like that. As our conjugate give you some extra information on the compact setting.
I see. Right. So yeah, there is a notion of compact V2 group you can define very easily in a strict two group setting. You can just say that it's a compact group point, and the source is also compact in some view. You can do that. But I don't know about Gawa this thing, but I expect something similar. Yeah. But
It's what we call, it has to quantize the level for.
that's
Because you have to know who did it to call out. Yes, but neither it takes a generic field. It's hard to say about that. So this is makes sense to first quantize do that and then consider it. It's still possible, but the first question I think is to contact for.
So I can say something like that. I can say a little bit more about like this relation of Q, which is that. So given that I can solve the so-called two-band vector, so okay. Well, okay. So given I can, so remember like this bimodule isomorphism. Like given I can solve this for in like UQG, right? Then what you can do is you can look at the kind of you can constrain. You can solve this guy in terms of this. So there's another kind of procedure in which you can do such that you're able to see the appearance of this guy coming from deformation of UG. You can deform this guy and then you somehow, so like, there's a possibility. Yeah.
Something like that.
Yeah, so something like that, yeah, but this is for two groups and the
two
groups. Yeah, the two algebras. But the idea is that R should depend on Q. And then what you can do is that you can, do the canonical thing, right? Like you write down kind of powers of this, and then you write down how many kind of different braidings that you can do. And you can use that to constrain essentially the number of equivalent reducible representations. You got it. And I think that this should be true, which is that if you need only finitely many If you want to say that pi 0 of Q rep H is finite, then this should quantize the law. Yeah, but like we need to like, yeah, but I feel like this should be true. Yes, yes.
To me, that's the contact that means finite. And you can somehow you can get, you can always get some.
Yeah, yeah. Mhm, mhm. Yeah, well, it's a good sign. You actually, well, I didn't actually say, well, I didn't say that like that whole UQG, that Hopf category. In what sense is it a compact quantum category, so to speak? I don't know. Yeah. All I know is that there's a notion of compactness for weak two groups, so, right? But as a category, it's kind of, because there's also this notion of compact category, right? Which I think it's a different thing. Okay, that's thank you again. Thank you. Thanks. Do we have people next week? Do we have people next week for a seminar? Next week, will there be speakers?
It's very fun one.